The second colligative property is elevation in boiling point, which is given the symbol delta TB. We know boiling point is the temperature at which the vapor pressure of a liquid becomes equal to the atmospheric pressure. But we also know the moment we add a non-volatile solute to the liquid solvents and the solution is formed, what happens is that the vapor pressure of the solution becomes less than the pure solvent. When the vapor pressure is less, therefore, definitely we have to heat the same solution to a much higher temperature so that its vapor pressure becomes equal to the same atmospheric pressure. This results in the increase in the boiling point of those solutions. And that is why this increase is called the elevation in boiling point. Now this increase is a colligative property, and the magnitude of this increase depends upon the amount of the solute in the solution and is independent of the nature of the solute. Let us see this with an example. Like we are already having a solvent A, liquid solvent with us, and to this we have added a B, a non-volatile solute. Now what happens is, we know we are having only vapors of A in the gaseous state, we don't have the vapors of the B. So vapor pressure of the solution, we already know the PS is less than P naught A, pure solvent. So what we find is, therefore we need to heat it to the higher temperature. This can be explained with the graph, the phase diagrams. The graph is plotted between vapor pressure and temperature. Suppose we have taken solvent A, whose temperature, whose vapor pressure at 25 degrees Celsius is found to be this value. This is our extreme value, which is 1 atm. Whenever the liquid's vapor pressure becomes equal to this 1 atm, it will start boiling. Now we started heating this solvent A slowly, and after increase in the with every degree Celsius increase in the temperature, we have calculated, we have determined the vapor pressure of the solution. So we started getting the points, and when we join all those points, we get a graph like this. So this graph is the graph of the pure solvent, and this at this point, if we draw the perpendicular, we can find out the temperature at which the original pure solvent starts boiling, because its vapor pressure becomes equal to the atmospheric pressure. This is called Ti. So what is Ti is called boiling point of pure solvent. Now, we again take the same solvent at the same room temperature, 25 degrees Celsius, and we add a non-volatile solute, B. Due to the addition of a non-volatile solute, already the vapor pressure of the solvent, now the solution, becomes less than the pure solvent. So at the same temperature, it is found to be here, A plus B. So this is your original solvent, this is your solution is. We started again heating this same solution now under the same conditions, in the similar conditions, and after every increase in the every degree Celsius increase in the temperature, what we are doing is we are finding out the vapor pressure of the solution. We start getting the point here, and when we join these points, what we find is that this graph follows this path. You can see here the temperature at which the original solvent used to boil, the solution is not boiling. The reason its vapor pressure is not equal to the atmospheric pressure. We need to heat it to a higher temperature. This is the point, we can drop the perpendicular, we can find out this is the temperature at which the solution starts boiling, and we call it TF. So your TF is boiling point of solution. Now this increase from Ti to TF is called delta TB, elevation in boiling point. So this delta TB is TF minus Ti final minus initial. This is called elevation in boiling point, and this can be very easily understood by this graph that this increase is the elevation in boiling point. And this is a colligative property, because experimentally this was found that it was found that this delta TB is proportional to M. What is M? Is molality of the solute in the solution. And the proportionality is opened by a constant which is called Kb, where Kb is called molar elevation constant or ebullioscopic constant. This is its name, ebullioscopic constant. And therefore, the actual formula of finding out delta TB is, we can expand this molality as WB MB 1000 upon WA. This is what we have as the delta TB, elevation in the boiling point. So this is what the formula is. And with the help of this formula, we can find out the elevation in boiling point when a non-volatile solute is added to the solution. Now this ebullioscopic constant or molar elevation constant is very important, and we need to know that every solvent has its own ebullioscopic constant values or Kb value, because it is actually are the interparticle forces of the solvent which determines where it will boil and where it will, how much it will, its boiling point gets affected due to the addition of that non-volatile solute. Now the unit of Kb can be determined as it will be equal to delta Tb upon M. So it is Kelvin kg per mole. This is what is the unit of Kb is. Unit of Kb. Now, in order to define Kb, if we take molality as 1 mole per kg, we came to know that Kb is equal to delta Tb. So we can define Kb as the elevation in the boiling point of the solution when, or boiling point of the solvent, when 1 mole of the solute is added to 1 kg of the solvent. Or the increase in the boiling point when 1 mole of a solute is added to 1 kg of the solvent is called the solvent's ebullioscopic constant. The value of the ebullioscopic constant is actually determined by this formula, RT square M 1000 over enthalpy of vaporization, where your R is your same universal gas constant, T is the boiling point of the solvent, M is the molar mass of the solvent, we can write Ma 1000, and enthalpy of vaporization is the amount of energy required to raise the temperature of 1 mole of the solvent by 1 degree Celsius or 1 Kelvin. So by this formula we can find out the value of the Kb, and every solvent is having its particular value of Kb, like Kb for water is 0.52 Kelvin kg per mole. It means when 1 mole of any solute is added to 1 kg of the water, this much of elevation in the boiling point of the water takes place. So this is what is your elevation in boiling point is, and yes, as it is proportional to the molality, we can find out how the molar masses of the solutes which are present in the solutions. The numerical is, find the boiling point of the solution when 36 grams of the glucose is added to 100 grams of the water. The ebullioscopic constant for water is 0.52 Kelvin kg per mole. Now from the given data, we already know that the weight of the solvent given is 36 grams. Glucose is C6H12O6, so its molar mass we know is 180 grams per mole. It's already, we know about this. Kb for the water is given as 0.52 Kelvin kg per mole, and the weight of the solvent is given to us as 100 grams. So we know the formula, delta Tb is Kb Wb Mb into 1000 upon weight of the solvent. So it's 0.52 into weight is how much? 36 grams upon 180 into 1000 upon 100. So this is 10, this is 0.2, this makes it 2. So it is 1.04. So elevation in boiling point is of 1.04 degrees Celsius or Kelvin, and we know delta TB to be equal to TF minus TI. TF is the boiling point of the solution, which we have to find out. Ti is the boiling point of the pure solvent, which we already know is 373. So we can find out this is to be 1.04. So TF is equal to 1.04 plus Ti, which is 1.04 plus 373, which is 374.04 Kelvin. So this is what is the boiling point of the solution is. And this is how we can use this information in finding out the boiling points of the solution or the molar masses of the solute which are present in the solutions.